Okay, this is exam 3 for physics 201 in fall 2010. It says Chad and Kaiser are spinning on a merry-go-round. Chad is on the outside edge and Kaiser is near the center. Which one has the larger centripetal acceleration? Alright, so you have this merry-go-round. Chad is here. Kaiser is here. Alright. And I want to know which one has the larger centripetal acceleration. Well, the centripetal acceleration is v squared over r. Now Chad has a bigger v, but he also has a bigger r, so it may not be immediately apparent which has the bigger centripetal acceleration. But we can say that v is equal to omega r, and if we plug that in here, we get omega r squared, which is omega squared r squared, over r, which just gives me omega squared r. So they both have the same angular speed, so the one with the biggest radius has the biggest centripetal force, so that is A, Chad. And this is witnessed if you ever ride on a merry-go-round, it's harder to hang on if you're on the outside, because that's because your centripetal force required is greater. This figure shows a truck on a banked curve and all the force vectors acting on it. A driver can safely drive at a higher speed on a banked curve rather than a flat curve. Which of these reasons is the correct explanation for why this is possible? Let's just look at them. The normal force for the car on the banked curve is less than on a flat curve. That's true because the normal force is equal to only a component of the weight. But that doesn't make you go faster because if the normal force is less, then that means that your static frictional force is less. So true, but not the answer. The weight of the car is greater on the banked curve than on a flat curve. Alright, the weight doesn't change. Right, the mass doesn't change, the weight doesn't change. On a banked curve, a component of the weight acts down the slope, thus increasing the centripetal force. Alright, now the weight, that is this force, has two components. It has a y component, Fwy, and then it also has an x component, Fwx. And it is this component that acts as a centripetal force along with the static frictional force. So on a flat curve, the centripetal force is just equal to the static frictional force. But on this, it's equal to that plus the x component of the weight. So this is the reason. Let's just look at the other. The static frictional force for the tires on a banked curve is greater than on a flat curve. That's not true. In fact, the static frictional force is less because the normal force is less. So you actually have less friction on a banked curve, but the component of the weight which acts down the slope improves or increases the centripetal force. So the answer then is C. An object is traveling in a counterclockwise circular path. At the point shown, the string holding the ball on the circular path is cut. What is the path of the ball that the ball follows after the string is cut? Alright, the answer is B. You take away the centripetal force, the object isn't going to travel in a circular path anymore. So A then is not the answer, nor is C. And it's going to travel in a straight line, which is the original state of motion. That's Newton's first law. The speedometer on my bicycle measures the angular speed and converts it to linear speed based on the radius of the wheels, which I input. Suppose that I input a radius that is smaller than the actual radius of the wheel. Which of these statements will be true? Well, we know that V is equal to omega R. The bike computer measures omega and then takes the radius that I input and calculates the speed, the linear speed, which I want to know. I read on the computer. So if R is small, then V is going to be small too. The speedometer reads in a lower speed than the true linear speed. Roller derby lady holds onto a rope that is tied to a post. She skates around the post and the rope gets shorter and shorter. If her angular speed remains constant, what happens to the tension in the rope? Alright, so this is very similar. A is equal to V squared over R. Alright, and I can also, it says that her angular speed remains constant, so that means that her speed is going to change because the radius is changing. So let's express V in terms of omega and R. So V is equal to omega R squared over R. So this is omega squared times R. So if omega is constant and R is decreasing, that means that the centripetal force is also decreasing, so that's C. Which of these arrangements provides the greatest torque? B has the biggest moment arm, so it's the biggest torque. Where can Kaiser stand to balance the board? You have Chad, who's a big guy, and then you want to put Kaiser. You see, if you put her down here at the end, she's not nearly big enough with the moment arm, which is a lot shorter, to balance the board. So there is nowhere, in fact, that she can balance the board. So the answer is D. While swimming near the bottom of a pool, you let out a small bubble of air. As the bubble rises toward the surface, its diameter increases. What happens to the pressure of the air in the bubble as it rises to the surface? Well, the pressure is going to decrease. This figure shows 4 identical C-shaped objects. Rank them in terms of least to greatest. And the objects, rank the 4 objects with the moments of inertia. So I say the least to the greatest, but the equality signs are down here. So let's look for the greatest one first. Remember that I is equal to the sum of mr squared. Alright, so we want to look for the one with the most mass at the biggest radius, and that's going to be B, because you got all this mass out at a big radius r. So this is going to be the biggest. So B is greater than. And the next one is going to be C, because you still have all this mass, you're just missing this part. Alright, so you have a similar but slightly smaller moment of inertia. So B is greater than C. And if you look at them, it actually turns out that C is equivalent to D. So B is greater than C, which is the same as D, and then A is our smallest. It's missing this mass out at a big radius. So this is greater than A. And let's see, that is A. Number 9 is A. In a mercury barometer at atmospheric pressure, the height of the column mercury in a glass tube is 760 millimeters. If the mercury in the barometer is replaced with water, what will be the height of the column? Alright, P is equal to rho GH. If you replace rho, the density, with that of water, that means that rho is going to be decreased a lot, so H is going to have to increase. So it's going to be greater than 760. That's C. The block of unknown density is floating in a fluid, such as in this figure. Which of these statements about the density of the block is true? The block is more dense than the fluid? That's not true, it would sink. The block is less dense than the fluid? Yes. In fact, it's less dense by a factor of 2. The block has the same density, and the block has more mass than the fluid. That might be true, it depends how much fluid there is. D. So the answer then is B. Blood enters a clogged artery, as in this figure. What happens to the pressure of the blood inside the clogged portion of the artery? Alright, well, the speed is going to go up because of the equation of continuity, so the pressure is going to go down because of Bernoulli's principle. So the pressure decreases. That's B. 12 is B. Standpipes along the top are used to measure the pressure. Where is the pressure greatest? Remember, pressure is equal to rho GH, and so this has the highest pressure. That is A. So you have pressure which is decreasing from left to right. Let me redraw that figure. Says that let's see, I'll draw the standpipes. We had the highest level here, next, and then the lowest. So our pressure, we have a big pressure, small pressure. So that means that we have a small velocity, or small speed, and a big speed. So if our speed is increasing from left to right, that means that the pipe is narrowing like this. So the pipe is actually narrowing from left to right. So the answer for that one is A. For number 14 is A. Alright, derive the moment of inertia for the rod in this figure. This is on the homework site, but I'll go ahead and do it. Just draw the picture of my rod. I didn't require you to draw this picture, but it helps. My rod is rotating about this axis, and my limits of integration are minus L over 2 to L over 2. And if this is my differential element, it's at a distance x, and it has a width dx. Now I want to determine or develop an expression for the moment of inertia of that differential element. My definition of moment of inertia is the integral of r squared dm, and I want to figure out what is the mass of that element dm. Well, dm is equal to the total mass over the total length times the length of our little differential element. Now if I plug that in, I is equal to the integral from minus L over 2 to L over 2 of x squared. I'm just going to change my r to x just to have my variables right. X squared times m over l times dx. Now my m over l comes out because it's constant, and so I have the integral of x squared dx times m over l, and the integral of that is x cubed over 3. Excuse me, it should be m over l. M over L x cubed over 3. My limits of integration are from minus L over 2 to L over 2. And then if I put those in, this is, I'm just going to take out the 3. M over 3L times L over 2 cubed minus negative L over 2 cubed. M over 3L L cubed over 8 plus L cubed over 8, which simplifies to 1/12 ml squared, which is the answer which was given. Alright, a disk has a mass of 10 kilograms and a radius of 2 meters. It's spinning at a rate of 3 revolutions per second. The disk is joined with a spinning rod of mass 3 kilograms and length 4 meters, so the rod rotates about its center. So we have this disk, and it's spinning, and then it is joined in some way with a rod. Alright, this is not uncommon when you're dealing with motors and engines and what have you, that you have these shapes, these objects of different shape coming together and transfer of momentum between the two objects. So I have these two objects and they come together and they're spinning around an axis like this. Now I want to know then what is their rotation rate after they're joined together. So I first want to find out what is their moment of inertia. The moment of inertia of a disk or a cylinder is 1/2 mr squared. That's 1/2 of 10 kilograms times 2 meters squared, which is 20 kilogram meter squared. And I for a rod is 1/12 ml squared, which is 1/12 3 kilograms times 4 meters squared, which is 4 kilogram meter squared. Now, I say that the initial angular momentum is equal to the final angular momentum, and that means that the initial is I of the disk times omega naught for the disk plus I of the rod times omega naught for the rod, and then that's equal to I disk plus I rod, because you're joining them together, times omega final. And I want to just plug in my numbers and solve for omega final. If I solve for omega final, it is I disk omega naught disk plus I rod omega naught rod divided by I disk plus I rod. Putting in my numbers here, I have 20 times 3. 20 is what I found up here. 3 is the initial spinning rate, 3 revolutions per second, plus 4 times the initial speed of the rod. The rod spins at a rate of 2 revolutions per second. This is in revolutions per second. Divided by the sum of the moments of inertia, that's 20 plus 4. And actually, I didn't count off much here. I'm not sure that I counted off more than a point or two, but it says that the rod spins at a rate in the opposite direction as the disk rotation. So the initial speed of the rod is actually negative 2 revolutions per second, just taking it to be the opposite of that for the disk. Most people didn't get that, and I don't think I counted off more than a point or two. So if I put in these numbers, I get 60 minus 8 over 24, and that's equal to 2.2 revolutions per second. That's the answer. Alright, flywheel has a mass of 3,000 kilograms and a radius of 4 meters. The wheel is initially at rest. Flywheel turns another gear which exerts a certain force on the flywheel at those coordinates, assuming the flywheel rotates about the origin. What is the torque acting on the flywheel? Alright, well, torque is equal to R cross F. Just want to know it in vector notation, so it's just doing the cross product. R, if it acts around the origin, R is going to be 1I plus 3J. And then F is given, that's 3I minus 4K. So doing FOIL, I get, well, first is 1I times 3I, but I cross I is 0, so I'll just leave that out. And then I get 1I times negative 4K, so that's negative 4I cross K. That's the outer. The inner is 3 times 3, J cross I. And then the last is 3 times negative 4, so that's minus 12, J cross K. And then it's just a matter of figuring out what are these. Again, I like to draw my coordinate system. This is I, J, K. And then I use my right hand rule. I cross K is equal to negative J. J cross I is equal to negative K. And J cross K is positive I. Alright, so now I just plug these in. So I have negative 4 times negative J, which is 4J. Excuse me. 4J. J cross I is minus K. Minus 9K. Minus 12I. And that's in Newton meters. Alright, how long does it take for the flywheel to reach a speed of 20 revolutions per second? 20 revolutions per second. So my final speed is going to be 20 revolutions per second. Just want to go ahead and convert this into radians. So in 1 revolution is 2 pi radians. 20 times 2 pi, that's 126. And I want to know what speed, or how fast does it take to reach, or how long does it take to reach that speed. Well, first I want to find the magnitude of my torque. Using the Pythagorean theorem, that's just 4 squared plus 9 squared plus 12 squared. Pythagorean theorem extended to 3 dimensions, and that is 15.5 Newton meters. Then I want to find out what is my angular acceleration. That's just torque over the moment of inertia. That's 15.5 Newton meters over the moment of inertia. Flywheel is a disk, so the moment of inertia, I'm going to do it up here, is 1/2 mr squared. That's 1/2 of 3,000 times 4 squared, which is 24,000. So this is over 24,000, and that's equal to 6.5 times 10 to the minus 4 radians per second squared. And then finally, we know that omega equals omega naught plus alpha t. Let's see, is it at rest? It is initially at rest, so omega naught is 0. So we just want to know what t is. T is equal then to omega over alpha, which is 126 over 6.5 times 10 to the minus 4. It takes a long time. 194,000 seconds is the answer for part B. Part B was worth approximately 10 points. It was the bulk of the problem. Now, how many revolutions does the flywheel rotate before reaching the speed of 20 revolutions per second? We know most of what we need here. Theta is equal to omega naught t plus 1/2 alpha t squared. Omega naught is 0. We just want to know how many revolutions. This is 1/2 times the angular acceleration. This is in radians per second squared, times 194,000 seconds squared, and that's equal to gosh, a lot. 1,223 followed by 4 zeros. Radians. And then you want to convert this into revolutions, and this is equal to 1.9 million revolutions. Alright, a block of aluminum has a density of 2,700 kilograms per cubic meter, mass of 10,000 kilograms. It sits inside a boat which is totally submerged when the block of aluminum is in its hold. When the block is removed from the boat, only 1/10 of the boat is submerged. What is the mass of the boat? Alright, you had to create a system of equations here. This is our first situation. Our aluminum sits in the boat. This is our block of aluminum. It sits in the boat, and the boat is fully submerged. Then you take it out, and the boat is only like 1/10 submerged. Alright. Now, we know in both cases that the weight, the full weight, is equal to the buoyant force because it's floating. The full weight, including the boat and the aluminum, is are equal. So this is the mass of the block plus the mass of the boat times G is equal to the density of water times the volume of the boat, and it's fully submerged. Alright, so it's the full volume of the boat times G. Now we can write a similar thing over here, that the mass of the boat times G is equal to the density of water times the volume of the boat over 10 times G. Now G cancels out in all of these equations. I'm just going to get rid of it. Now I can solve this for the volume of the boat. It's equal to 10 times the mass of the boat over the density of water. You can take this and plug it in over here for the volume of the boat. So if I do that, I get the mass of the block plus the mass of the boat equals the density of water times 10 times the mass of the boat divided by the density of water. I'll just substitute that in for the volume of the boat. Get rid of some things. Volume of the water, the density of the water goes away, and I combine like terms. The mass of the block then is equal to 9 times the mass of the boat. So the mass of the boat is equal to 10,000 over 9, which is 1,100 kilograms. Alright, water is traveling in a pipe with a cross-sectional area of 0.2 meters squared. Speed of 3 meters per second. The pressure in the first pipe is 3,500 pascals. The water goes into a second pipe and the pressure goes up to 4,000 pascals. What is the area of the second pipe? Alright, so I'm not going to draw anything, so it might just confuse you. So P1 is 3,500 pascals. V1, 3 meters per second. P2 is 4,000 pascals. We want to know what is V2. Okay, so we know if the pressure goes up that the speed is going down, and so that means that the area is going to increase. So we're looking at a situation where our pipe does this number in order for our pressure to increase from left to right. So we first want to use the Bernoulli principle. That is that P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. And put in our numbers, we have 3,500 plus 1/2 of 1,000 times 3 squared is equal to 4,000 plus 1/2 of 1,000 times V2 squared. If we solve this for V2, we get V2 is equal to the square root of 8,000 minus 4,000 over 500. I'm skipping several steps, so you want to go back and do your algebra. And this is equal to 2.8 meters per second. So that's my V2. This was half the problem. The other part of the problem is what is the area in the second part of the pipe. Well, now we know what V2 is. We know from the continuity equation that A1 V1 equals A2 V2. So just putting in our numbers, A1 is 0.2 meters squared, so 0.2 meters squared times V1, which is 3 meters per second, is equal to A2 times 2.8 meters per second. Solving for A2, A2 is 0.214 meters squared, or 0.21 meters squared. Alright? Most people got this right.